Welcome, AP Physics C students, to our first unit of second semester, starting off electricity and magnetism. We're going to talk about electrostatics today, electric force, and some charging methods. Later on, we'll look at electric fields, and then the second part of this unit will cover Gauss's law. Up at the top of your notebook, we have a French postage stamp of Charles Augustin de Coulomb. If you can see the dates at the bottom of the stamp, he lived from 1736 to 1806. Mr. Coulomb was a officer in the French army. He was an engineer in the army and achieved the rank of lieutenant. He was also a physicist and is best known for his discovery of what we now call Coulombs Law. Coulomb's law is a formula very similar to Newton's universal law of gravitation, which can be used to predict the force of attraction or repulsion between charged particles. 74 years after his death, the SI unit of charge was also named after Coulomb. So an important guy. We'll talk about some fundamental ideas. Charge is quantized, first of all. That means charge only occurs in discrete amounts. You can have zero charge. You can have 1 E. E is the elementary charge. And the elementary charge is the amount of charge on a proton or an electron. An electron has a charge of minus 1 E. A proton has a charge of plus 1 E. And you can have integer values of charge, 1E, 2E, 5E, 17E. You may not have 2.5E or pi E or some irrational amount of E. You can't have square root of 2E charge. They only come in discrete integer values. So that's what we mean when we say charge is quantized. A second idea is that charge is conserved. That means the total amount of charge won't change, but it can be transferred between objects. We've seen several conservation laws already previously in physics, such as the conservation of mass and conservation of energy, conservation of momentum, conservation of angular momentum. Each of these conservation laws has its own set of requirements as to when it is true and when it isn't true. Now, conservation of mass and conservation of charge are pretty much always true in the AP Physics curriculum, although when you look at things at a deeper and deeper level, you often find out that what was taken for granted or as truth at one level turns out to be, have its limitations in other levels. So mass can be created and destroyed. It can be turned into energy. That's Albert Einstein was associated with, E equals mc squared, and it turns out that you could create or destroy charges, but that would be something that would be studied more in other areas of physics that aren't covered in Physics C. So for now, mass is conserved, charge is conserved. It can be transferred between objects, and when it is transferred between objects, it is electrons that get transferred. If you had ionized fluids or gases or liquids, then positives could move around. In a plasma, positives could move around. But for our purposes in Physics C, we are only going to be studying solids. So anytime charges are exchanged, it is going to be done by the transfer of electrons, and you will never transfer protons from one object to another. The SI unit of charge is the Coulomb, and we'll talk a little bit more about that coming up. And lastly, opposite charges attract. So a positive and a negative charge would attract. Right? They will be attracted to each other. Same charges will repel. So if you have a plus and a plus, they're going to want to go away from each other. Same with a minus and a minus. They are going to get repelled. A neutron is going to experience no electrical force. However, neutral objects can experience electrical forces through polarization, which we'll talk about later. So don't get neutrons, which don't experience force, confused with neutral objects, which could experience a electrical force. All right, moving on. Over at the left here, we've got Coulombs constant. 9 times 10 to the 9th, the units for that, Newton meter squared per Coulomb squared. Another way of writing Coulomb's constant is 1 over 4 pi, and then there's this Greek letter down here, epsilon naught. Epsilon naught is the vacuum permeativity. Now, what is the vacuum permeativity? Vacuum permeativity is a measure of how electric forces and electric fields exist in a vacuum. The vacuum permeativity is also related to the speed of light. The speed of light in physics is represented by the letter c, and c is 1 over the square root of epsilon naught times another constant mu naught, which we will study later in the semester, that relates to magnetic fields in vacuums. Now, it shouldn't be a surprise that the speed of light is related to how electric fields exist in a vacuum and how magnetic fields exist in a vacuum, since light is itself an electromagnetic radiation. It is comprised of an electric field and a magnetic field. So, of course, it's going to be related to both of those. Epsilon naught is the permeativity of free space. Mu naught is called the permeability of free space. Permeativity of free space, permeability. I really don't like how close those names are, and it makes them difficult to keep track of. So be aware that we won't get to study the permeability of free space until we get to magnetism, which is going to be towards the end of the semester. Also on the equation sheet, you've got the mass of a proton. Notice it's 10 to the negative 27th kilograms, not very massive. A proton has a charge of plus E. A neutron has the same mass as a proton, but it has no charge. An electron has much smaller mass than a proton. Look at these exponents, negative 27, negative 31. That's several orders of magnitude less. I think it's somewhere around 1,800 times less mass than a proton. So basically, the mass of an electron is negligible compared to the mass of a proton. An electron has a charge of minus E, and E itself is the fundamental charge. It has a value of 1.6 times 10 to the negative 19th coulombs. Now, that fundamental charge there, that can be used to come up with a ratio for conversions. Unit conversions. If you want to go from coulombs into elementary charges, you would multiply by 1e for every 1.6 times 10 to the negative 19th coulombs. And if you wanted to go from numbers of electrons or protons to coulombs, you would multiply by the reciprocal of this. 1.6 times 10 to the negative 19th coulombs is 1 elementary charge. And by doing some dimensional analysis, you could figure out that the units would cancel. So these are unit conversions that you could use should you need them. I haven't seen a lot of these type of conversions in Physics C, but maybe. We have Coulombs Law here. Coulombs Law on the equation sheet, on the equation sheet, it's given as a absolute value, which means we're dealing with the magnitude of the force. You can relate Coulomb's law using either the vacuum permeativity or Coulomb's constant. I find this is easier because it's just less typing on your calculator. So I generally use this when I'm figuring out an amount of electrical force. And just like universal gravitation, it's some constant times the magnitude of two charges divided by the radius square. So this is an inverse square law. If you double the radius, you're going to get 4 times less force. If you bring the charges 3 times closer, you're going to get 9 times more force. Then we have a formula down here for electric field, which is electric force divided by charge. That is to say, the force per unit charge when you divide them. Another way of writing this would be to take this equation here, which is force, right? Take this equation and divide by Q. When we divide by Q, it's going to cancel out one of these Q's, and we could say that this is KQ over R squared. And I like to think of this again as absolute values, magnitudes, and then we can think about the direction the electric field points separately. So for the electric field here, the electric field is defined to point in the direction a positive charge is forced. Whichever direction the force is on a positive charge, that is the same direction as the electric field at that point in space. We'll talk more about the electric fields later. And then this formula here, which is integral calculus, will tell you the electric field from a continuous distribution of tiny charge elements, dq. So this would be like an entire charged rod, or like a ring of charge, or a semicircular arc of charge, something like that. You could use this integration to figure out the electric field by essentially making it into an infinite number of point charges and adding them all up. And of course, you could replace this 1 over 4 pi epsilon naught with a k as well. So next, some information about Coulomb's law. Coulomb's law, we should remember that opposites attract. Maybe not in life, but in charges, that's true. So a positive charge and a negative charge, they will experience an attractive force. Like charges will repel. So if you have a positive and a positive, they are going to push each other away. Similarly, if you have a negative and a negative, they are going to push each other away. And with Coulomb's law, we should get the magnitude of the force from the formula. And of course, magnitude means ignore any negatives that you get along the way. So when you're plugging your numbers in and putting it in your calculator, don't even put negatives, just make both of the charges positive. So we get the magnitude of the force from the formula, and we can think about the direction of force separately. And when we think about the direction, we're going to be using this stuff about opposites attracting and like charges repelling. These next few examples, we're going to do these in class. I'll teach you some calculator tricks and stuff to make these go faster. These will be done in class. We got this balloon charging lab that we'll do in class. We're going to skip forward and look at materials and polarization next. And you're going to research and define these terms on your own. Okay? I'll say a couple words about them, but you can kind of finish it up. A perfect conductor is something that allows electrons to move completely freely without any resistance, without anything to slow them down or get in their way. A conductor is something that allows electrons to move freely. These would be metals. Semiconductors are used in computer chips. Insulators do not allow charges to flow. They do not allow charges to be conducted very easily. Now, anything can allow the flow of charge if you push hard enough. Everything has its limit. So a perfect insulator would be a material that does not allow the flow of charge at all, no matter how hard you push. That doesn't exist in reality. It's more of a conceptual idea. So perfect conductors up at the top would have no insulation and they would have infinite conduction. And a perfect insulator down here would have no conduction. It will not allow electrons to flow at all. And it would have infinite insulative properties. All right, moving on at the bottom of the page, we're going to talk about polarization. So let's define polarization first. When something is polarized, it means that we have a separation of charges. And this can exist in any material. So all those materials that we just talked about, from conductors to insulators, conductors can become highly polarized. Since a conductor allows electrons to move, essentially many of the electrons can move over to one side of the material and positives would remain on the other side. You can see an example of that here. We have a glass rod that is positively charged. We bring it near a conducting sphere, and a lot of the electrons will migrate over to one side. This is not nearly every electron in the conducting sphere. Only some electrons are free to move, but just some is enough to produce a noticeable effect. So conductors can be charged. And when you charge a conductor, you have a large charge separation in a conductor. So conductors can be polarized. And so can insulators. Now, an insulator being polarized is essentially how a balloon sticks to the wall. This didn't copy so well, but when we take a balloon which has negative charges on one side, the molecules in the wall are going to become slightly polarized. Now, this is just an effect that takes place atom by atom. These electrons here are going to take the electrons at the edge of the wall and kind of repel them, and they're going to spend more time on the other side of the atom than they do on the outside wall of the wall side of the atom. So it's a small effect, but it's enough for the balloon to want to stick to the wall. You could think about the atoms in the wall like almost rotating a little bit, or just think about the electron clouds shifting over so that the electrons spend their time away from the surface of the wall, and that leaves the surface of the wall a little bit more positive. But what does not happen is that the electrons flow all the way across. They generally stay with their atoms. They just spend more time on one side of the atom than the other. So although this is polarization, it is not as great of an effect. And we have here a tiny shift in the electrons of the wall. Over on the left side of our page, we have an example of water. This is H2O. And because in H2O, the electrons are shared, they spend more time on this side of the atom. And remember, the oxygen atom here has electrons all over it. But because these electrons are spending more time over here, it leaves protons exposed here. So this side of the molecule has kind of a net positive charge, and this side of the molecule has more of a net negative charge. So if we wanted to, we could think of this atom as being like this, where this side would be more negative, this side would be more positive, and we would say that water is a polar molecule. Now, there is something called the dipole moment. And the dipole moment is a measure of how polarized an arrangement of charges is. And we got one more little note that we're going to make here. I'm just going to isolate this off a little bit. Down here at the left, we have a capacitor. Now, at the top, this is unpolarized, and this would be polarized. You can see that in the polarized arrangement, the random atoms have now kind of aligned themselves, so the negatives all point one direction and the positives all point towards another side. And we'll talk about capacitors a lot more in Unit 3 this semester, but we'll just make a note here that in capacitors, special insulators called dielectrics. Oops. Electris. Dielectrics are polarized and used to increase energy storage. We'll talk more about that later. And that kind of wraps up this page. So next, we're going to talk about ways to charge objects. You've already experienced some of these in class, starting with charging an object by friction. On the left here, we have a polyethylene rod, a dry cloth. We rub them together. The rod pulls electrons off of the cloth, meaning the rod will have a negative charge afterwards, and the cloth, there's still electrons left on the cloth. The rod does not take all of them, but the cloth now has more positives than negatives, so its net charge is positive. And the rod has more negatives than positives, so its net charge is negative. How do you know which one becomes positive or negative? That's based on what we have here, the triboelectric series. When you have a material at the top of this series, it wants to become positive when it's rubbed. So these will tend to lose E minus, and they will tend to become positive. Lower down on the list, these materials want to gain electrons, and they will tend to become negative when you rub them together. You can rub any two of these materials together and you get some effect. So for example, if I was to rub like sulfur and polyester, that would have a low effect because they're pretty close together on the series. The one that's lower down is going to become negative. So the polyester would become negative, the sulfur would become positive, but you wouldn't see a large amount of charge transfer. However, if I was to take some other objects here, like wool and silicone, that would have a large effect because they are far apart. The wool would tend to become more positive, and the silicone would gain a lot more electrons because they are farther apart. That's a little bit about how the triboelectric series works. That's one way of charging, is charging by friction. And when you rub the objects together, electrons fall off of one and kind of jump onto the other. Another way is charging by conduction. To charge by conduction, it works best with metals. You can kind of charge an insulator by conduction, but only a very small part of the insulator. So here, I'm going to make a note that this metal sphere and this metal rod, that those are going to be metal conductors. And what we have is electrons flow off of the rod onto the sphere, and then the sphere becomes charged. If you had a rod which was an insulator, only a few electrons from the very tip would flow off, and the sphere would not become very charged. So it works best if you have a metal rod with a metal sphere, and both of them are conductors, and then you can get lots of charge to transfer, or at least more than you would otherwise. In this image here, we have a plastic and metal. I'm going to do some color coding here. I'm going to first draw some positive charges in red. Each of these starts off with about the same number of positive charges. I'm going to draw negatives in blue. And if I was to bring a positively charged rod nearby in the plastic, nothing's really going to change. The charges are not free to move in an insulator, so they will stay the same. Maybe this surface gets polarized a little bit. Maybe, just a little bit. But in the metal where charges are free to move, this positive is going to attract the electrons of the metal sphere over to the left, and the positives are going to have an excess over on the right. Now, I'm not showing all of the positives and negatives here. That would be impossible. I'm just showing the excess. So the electrons have all moved over to the left, and what that does is leave positives on the right. The positives did not move over to the right side. It's the electrons that move to the left, and the positives then remain on the right. And there are still negatives here on the right. There are just more positives than negatives. I want to make a quick note about this. The insulator is slightly polarized. Slightly polarized as the electron clouds move a bit in response to the rod. In the conductor, we have electrons flowing from side to side, and it produces a much larger and a much more dramatic effect. The third way of charging that we're going to cover is charging by induction. That is charging a neutral object without actually touching it with a charged object. It still involves things touching, but the objects that are acquiring charge don't actually ever touch a charged object themselves. They're just brought near to a charged object. So we'll look at two examples of that. On this page here, I'm going to label the sphere on the left A and the sphere on the right B. And I'm again going to show some positives and negatives here. In part one here, sphere A is polarized and neutral. And sphere B is just going to be neutral. So sphere A is going to have, the rod here is negative. That's going to make the electrons repel. The electrons are going to go over to the right side, and that leaves positives over on the left. In B, they're going to be symmetrically distributed. Now, when we bring the two together, the electrons get repelled all the way as far away from that rod as they can. They're going to go all the way to the right. And in this situation, A and B act as one large polarized conductor. As soon as they're touching, they act just like one object. Now, when we separate them and the rod is still there, we've essentially trapped those excess electrons over on the right. But because sphere B is farther away than sphere A, those electrons are basically going to be symmetrically distributed. So we can say that A is now charged. Here's if I could write and talk at the same time, that would be nice. Charged and let's not say polarized, let's say unsymmetric. Charged and unsymmetric, where B is charged and symmetric. Again, speaking and writing, 1T, symmetric. And then when the rod gets moved completely away, these charges on A will redistribute themselves symmetrically. The charges on B are going to be symmetric as well. And we would say here that A and B are charged and symmetric. And this part about being symmetric here, that kind of depends on the distance between the two spheres. If these spheres were closer together, then the charges would tend to reside more on the sides as they get attracted to each other. The farther apart they are, the more symmetric the charge distributions will become. All right, we got one more example to look at. And this example involves ground. Grounding is a connection literally to the Earth, and the Earth is so large that it can basically give or receive a near infinite number of electrons and remain essentially a neutral object. You've probably heard of a lightning rod. A lightning rod is just a glorified grounding wire. What a lightning rod does is allow a lightning strike the easiest path to the Earth, so that rather than going through a building, it goes through a conductor, which is large enough that it doesn't melt, and the lightning just sends the electrons straight into the ground, and the Earth absorbs them, no problem. Now, in this example, we have a negative rod brought near two metal spheres. We would say that these metal spheres are polarized, and the positives are going to be on the left side because the negatives are getting repelled away from the rod. Now, when the right side is grounded, what it does is give those electrons a path to the Earth. And they're going to leave altogether. And now this right sphere is essentially neutral, and this sphere has an excess of positives. When we remove the grounding, we still have an excess of positives on the left side, but everything else is essentially neutral. Now the negative charge is removed. These positive charges are going to distribute themselves symmetrically because they repel each other. Now, remember, the positive charges aren't actually distributing themselves. What's happening is that the electrons that were over on this side, some of the electrons are getting attracted to these protons. So some electrons from over here got attracted and it left an excess of protons on the right side. It's always electrons that move in these situations. When we separate the rods, they both have a symmetric positive charge distribution. And then at the very end, when we have this leftmost sphere connected to the ground, that allows electrons to come from the Earth. And so now the left sphere is going to be neutral and symmetric, while the right sphere is still going to have its positive charges, which would be symmetrically distributed. I think that covers everything for the first part of this notebook. Thank you for following along, and I look forward to seeing you soon.